Hello student, welcome to our physics discussion, that is physics in a smart way. Today we go to a rule of thermodynamics, one of the most fundamental rules that is known as the first law of thermodynamics. Of course, there is another law and it was found out, it was discovered after this law was developed, the law that is mentioned, the so-called first law, but, but subsequently it was found that law should be placed before the first law is mentioned. So that was marked as zeroth law. Zeroth law. We do not have any need of going to now. Our basic the basic need is to go for the first law. So we go for the first law from Alex for a long time that it remained as the first law. Zeroth law came a bit later. Also that has got bit less practical significance. So for a first law of thermodynamics is there. It can be expressed into forms. One is macroscopic, second is microscopic. That is usually in the form that Q equal to delta U plus W. Sometimes book write as W, sometimes delta W. That doesn't make so great a difference. Or in microscopic form, in small form, dq equal to du plus dw. Usually it is mentioned that the first law of thermodynamics is first law of thermodynamics is based on energy conservation. Energy conservation, as you remember, the energy conservation or conservation of mechanical energy in work, energy, and power. But this type of statements, and usually in every book that you go where the first law of thermodynamics is mentioned, they mention that it is based on energy conservation, but that creates a confusion in the mind of the student. Whenever I see the word energy conservation as a student, we know conservation means a sort of constancy, constant, something is conserved. So the student might be getting a false idea that the thermal energy or the heat or energy is conserved. But in fact, the case is not so. In fact, it will be much better if the people of science sit together and they they sorry they combinedly take a decision that this conservation word is replaced by the word balance. Then that can convey much better sense. The point is that when somebody says energy balance, the thing becomes very simple, just like a banking balance sheet, just like the financial balance, even if your that is pocket money balance. Pocket money balance. You are a student. If it is assumed that you start from your house or home every day, go to your college or school, and then come back in the evening. If you take the case of a student, then you do know that, let us say, the student is given at the start of the day when he or she goes to the class a sum of rupees 100. He or she consumes 60 rupees out of that, and when he or she gets back, he has to show them the surplus amount or the remaining amount, that is 40 rupees, because 100 must be equal to 60 plus 40. Nobody can violate that, not even God. Maybe God has created this rule or created this equation, but he cannot find it. Immediately, the student, if he or she doesn't show 40 rupees, then he or she will be asked a question that you have been given 100 rupees and you claim that you have spent 60 rupees. You must show 40 rupees. 40 rupees, you can keep it with you or return to your mother or father, doesn't matter, or spend in some way at your home, doesn't matter. But 100 must be equal to 60 plus 40. That's a balance statement. That's a financial balance statement. Just like the banking balance statement of the day, a bank must be having some money at the start. During the daytime, people will be starting to deposit in the bank. So thereby deposits will be coming in. Some people will be withdrawing. So withdrawing means that's a negative thing for a bank because money goes out. So if somebody says that the final amount that the bank has got now at the end of a day will be equal to initial amount or initial stock plus deposit minus returns. You know, this cannot be violated by God even if God has created that, because it's a balance statement. So first law of thermodynamics is just like a balance statement. That doesn't say that thermal energy or heat or energy will be conserved inside a gas or inside a sample like that. It says that we must be knowing how to have a perfect account of it. You must be able to account it, just like 100 rupees, 100 equal to 60 plus 40. When your parent give you 100 rupees and at the end of the day you return them 100, they will be angry. Instead of showing pleasure that you have been given 100, you have not done anything. You have not taken anything, you have not eaten anything, all those things. So your parents doesn't want that. You will be conserving the 100 rupees. But the parent want that they must be seeing the account of 100 rupees, how you have spent and what is the breakdown. That is the basic essence of your first law of thermodynamics. So it says that if a gas is given a thermal energy or heat Q, then it can be consumed in two ways. Part of the heat can be stored in the gas in the form of internal energy. Internal energy. As a result, temperature must be going up because internal thermal energy of a gas goes up. So thereby temperature goes up. And partly, the remaining part, gas can do some work and send out, or the gas can do the work on somebody else, then send out it outside. My point is that, my point is that if you refer to the diagram, we just look at the diagram. So here what we got, a gas is given heat or thermal energy. As a result, the gas, because it acquires heat or gets heat, its temperature increases and it expands, and the cylinder is fitted with a pitting piston, type pitting piston, and the piston head is connected to a spring. As a result, as the piston goes up, the spring is getting compressed, and because the spring is getting compressed, there is a energy stored in the spring or work done on the spring. You know the formula that must be equal to half k square. So thereby, if you try to put the macroscopic form, because here we show everything significant, not very small. So Q equal to delta U plus W. We know this Q is nothing but heat given by us. Delta U is the change of internal energy, which can be found out very simply by using the formula, because that formula will be discussed later on. That is, that has got a formula of N CV into del T. N CV into del T. N is number of moles, CV is specific heat and constant volume, and del T is the change in temperature of the gas. That is the change of internal energy for any gas. Plus W. W is the work done. W is the work done by the gas, by the piston on the spring. Because if you ask the spring, and of course, if you are able to converse with the spring, have you got energy? Then the spring says, yes, I got energy, but previously I was not able. Who gave you energy? The gas gave you energy. Where's the gas? Because it compressed me now. I am in a discomfort now. So thereby, the work done must be equal to the stored energy inside the spring, because the gas does some work. If in place of it, we do some work, you do some work on the gas, then that work will be having opposite nature. Thereby, the external agency which is doing work, we know that is feeding energy. That would have added up with Q, and thereby both of them would have resulted in increase of internal energy. Okay, clear? That is the idea of the first law. So the first law is not about the so-called conservation as normally we take it. It is a balance statement. The gas is not supposed to conserve or keep intact anybody, just like we throw up a ball inside a gravity field, and whatever energy we give to the ball, that energy remains conserved and all that. Here, the case is slightly different. You have to be liberal. We know the energy balance equation must be valid, okay? And this can work in opposite way also. As I told you, you can give heat to the gas, you can take out heat from the gas. So thereby, as a result of that, internal energy must be falling, the stored energy must be falling, temperature must be falling, the gas is usually compressed, the gas volume usually decreases. So all those things happen. That those will be seen when you go for some questions, go for some problems. So that is good. Later, initially we must cover all the formulas like these and all those things. Okay. So thank you for your kind cooperation. Please like, please share, please subscribe if you find anything of value in it. That's all for